Okay. Half the people were the family members of our speaker. And the food finally came about 7. And then it was raining outside. And these folks, they're from Arizona. So I guess the kids haven't seen rain before. So running in the rain, and one of them hurt her knee and needed some first aid. Yeah. So anyway, thanks for waiting. And we're lucky because our speaker just flew in last night from Arizona. And not just for the meeting, but it'd be nice if it was, but it kind of reminds me of last month's meeting. If you remember, the speaker for that meeting flew in the afternoon of the meeting from Japan. Yeah. But not just for us. But our speaker tonight, this is Bob Boville, who was a software engineer on the Rubin Observatory in Chile. And it began surveying the southern skies just this month. You might have seen some of the preliminary pictures that have been in the news. Originally, it was designated as the Large Synoptic Survey Telescope, LSST. And but then it was renamed more recently in honor of Vera Rubin, the astronomer. So this telescope was originally envisioned as a resource for studying dark matter, but there's other mysteries that it's involved with too, and we'll hear about those in a minute. So are you ready, Bob?
I'm ready.
All right, thanks.
Right.
Is it Bob or Rob?
Rob. Presentation, a moment to load up. All right. I guess the first question is, can everybody see and can everybody hear me? I guess especially the folks online. Can they hear me from there?
They should be able to, because we did a sound check, and they're saying, yeah, because we did a sound check before.
Okay, great.
Thanks, Rob.
All right. Hey, thank you very much for inviting me to speak to you tonight. And today I'm going to be talking about the Vera Rubin Observatory. Which is a very unique telescope with a very unique mission. And we'll go ahead and get it started. I'll talk a little bit about myself to start off with. So I'm from Portland, Maine originally, and got my bachelor's degree in physics from the University of Maine in 2003. I moved to Tucson immediately after for graduate school. I did 2 years there, also in physics, but have always had a preference for astronomy. So I have a minor in astronomy and took a lot of the astronomy classes for that degree. Around that time, the University of Arizona was awarded the first opportunity for a university to run a space mission, and that was the Phoenix Mars lander that touched down in early 2008 and did its work for a couple of months. It was in the northern polar region of Mars. And when the winter set in, that was the end of that mission. I currently live in Tucson with my wife and 2 daughters who are here, as well as my sister and her family who live in Baltimore. And I work as the telescope and site software test engineer for the Vera Rubin Observatory. It's quite the mouthful, I know. What does that mean exactly? So I set up and maintain our Jenkins continuous integration, continuous discovery development environment. I administer our GitHub and Docker organizations. I oversee our Nexus repository manager. And then, of course, as a test engineer, I am writing and executing tests on the control software. So the telescope and site group of the mission is responsible for everything involved with the telescope operations and the site operations. We distinguish that from the data management side of things, which I will get into a little bit later in the talk. So if anybody has any particular questions about what I do, that is what I focus on. A couple of things of note. My background is in physics and astronomy. I work for 3 different telescopes. I didn't mention it on here, but I've been doing outreach for quite a long time. So my day job, as I said, is the software engineer for an 8.4 meter telescope. I also run outreach programs at the top of Mount Lemmon, which is one of the highest peaks in Tucson, and how I met Vanessa, actually. We both work for the Sky Center there. That's a 1 meter telescope. And then additionally, we run outreach for a local resort, and they have a 9-inch telescope. So even though I work for 3 different telescopes, I don't know anything about optics. So if you have questions about what we're seeing in the field of view of a telescope, that I can help you with. If you have questions about how we're seeing it, I can't help you that much. So this was a picture of the facility around 2019. So we're still in the middle of construction when the pandemic hit. So that's a little context there. But that is our mission statement up there. I will give you a moment to read that. And here's how the project is broken down. We have the project facilities located in Chile, and then the headquarters are in Tucson. And that is an NSF-funded project. That's the Vera C. Rube Observatory. A little odd, the camera was separately funded through the Department of Energy at SLAC. So even though it's one observatory, the site and the facilities were funded by the NSF, and the camera was funded by the Department of Energy. But once combined, as they are now, they will conduct in the first 10 years of operation what's called the Legacy Survey of Space and Time. And if that sounds strange, it is. There's a very good reason for that. Originally, the telescope was named the Large Synoptic Survey Telescope, LSST. And that acronym is baked into our networking. All of our email addresses are LSST. All of our computers are named with .lsst.org addresses and such. And so we needed to maintain that acronym. And so when we rebranded the telescope in honor of Vera C. Rubin, we referred to the first 10 years of operation by the Legacy Survey of Space and Time, which has the same acronym, LSST. So that's the reason for that. Just a little breakdown of the funding. The NSF was responsible for almost $600 million for the site and facilities. The DOE through SLAC, a little over $150 million for the camera. And then we also have an organization, the LSST Corporation, which was responsible for processing private donations and monies that way to help fund the project as well. So in a nutshell, what I'm going to talk a little bit about today is the telescope itself, the 8.4 meter telescope. We'll talk about the 3.2 gigapixel camera, a little bit bigger than the camera in your cell phone. We'll go into a little bit of detail on the data processing, data management side of things. I'll point out the public engagement, public science side. We actually do have a large citizen science contingent. So as soon as I'm done my talk here, you can actually jump on over to the citizen science site and start investigating. The camera is expected to take about 5 million images and catalog more than 37 billion objects. Each night will have millions of alerts. We'll get into what all that means. But in the over the course of the 10 years, we expect to generate tens of billions of events that software and graduate students and future scientists will be investigating for decades to come. It's located in the southern sky, so it's going to image the southern part of the sky, and any arbitrary patch of the sky we expect to be imaged at over 800 times over the course of the 10-year mission. So why Chile? Well, there are three main components that make a site ideal for astronomy viewing: high, dry, and remote. We're built upon the Cerro Pachon Mountain and the Andes Mountain Range in La Serena. So we're at about almost 9,000 feet. Very dry, only about 42 millimeters of precipitation each year. And it's remote, but not too remote. The mountain range itself is pretty remote, but La Serena is about an hour's drive from the peak. So La Serena is a decent sized city, almost 300,000 people. And then a couple other key points. Politically amenable. I use that term to just mean that Chile itself, the Chilean government, has actually opened its borders to the astronomy community, making it very, very easy for astronomy institutions to set up and build telescopes. In fact, Aurum, the parent company, has many, many facilities. In fact, there are just a couple of facilities on very nearby peaks. And some of the images, you'll actually be able to see some of the observatories that are right next to the Rubin Observatory. And then, of course, good climate, no extreme weather, no natural disasters. The site is prone to earthquakes, so we do have mitigations in place for that, but nothing terrible, nothing to classify as a natural disaster. And then also had to keep in mind if the area has any significance to indigenous populations. And so all of that combined, we settled on Cerro Pachon in Chile. There are 4 science goals that Rubin will focus on: dark energy and dark matter, solar system cataloging, Milky Way structure and formation, and transient objects, transient events. That's actually the key focus. We'll get into how Rubin Observatory optimizes for transient science. But first, we'll talk a little bit about each of the science goals and what exactly LSST, and the camera and the observatory itself will be doing. So dark matter is just matter that exists in galaxies and in the universe that doesn't emit light. We don't see it in detections, but it has gravitational effects on the matter we can see. And so we know it's there, we just don't know exactly what it is. And so one of the goals is to, if not identify what it is, at least be able to narrow down the parameters of what is dark matter, since we know it makes up 80% of the universe and affects how galaxies and the universe as a whole formed. In fact, if you look at the next image here, this is kind of an image not from our telescope, but a large-scale structure of the universe. And so you can see that there is some structure to it. There are galaxies, those are the points of light that are in clumps, and then there are some isolated clumps. And dark matter affects how those clumps evolved, and dark matter also affects how the galaxies ended up in the filaments that they're in. We'll also be, just because we're scanning so much of the sky so rapidly and with such a large field of view, just kind of for free, we'll get a lot of data about solar system dynamics. So we expect to catalog, many, many times more objects than are currently known, and most likely further and farther away out into the Kuiper Belt. So you got to get a sense of where those objects are that we'll be getting to take a look at. So we also want to start investigating the formation of our own galaxy. And as I kind of mentioned when we're talking about dark matter, galaxies start as these small clumps of dark matter, regular matter, And then eventually these halos will merge to form larger and larger galaxies. Some of these mergers are actually recent enough that we can detect some of the remnants and after effects of those mergers. Advance to the next screen real quick. So this is the pretty famous Whirlpool galaxy. And you can see in the lower corner there, there's the connection, the stream of material between those two galaxies as they merge. As the process continues and the galaxies do end up merging into one and you can no longer distinguish the two, you can still see remnants of that streak, of that material encircling the galaxy. Currently, the Milky Way has 23 of these streams that are known, but Rubin will be powerful enough to observe and identify even more of these streams. And the more data we gather about these phenomena, the better we'll understand the formation of our galaxy and presumably galaxy formation in general. And then transient objects. This is really the key to the Rubin Observatory. Most telescopes, in my experience, are really designed to pinpoint a single small patch of the sky, a star, some very small discrete object in the sky, and observe it very, very carefully over a long period of time. Rubin does not do that at all. Rubin has a much larger field of view, which we'll get into in just a few moments, and is scanning the sky much, much more rapidly than most telescopes. So as I said, we're going to be averaging over 800 times imaging any arbitrary patch of the sky. And this will allow Rubin to identify over 10 million changes on a night-to-night basis, 100 times more than current telescopes. So we'll be focusing on solar system bodies that change position, and then, of course, anything that changes brightness for any reason. Variable stars, supernova, mergers of neutron stars, black holes, things like that. So just a couple of images of some of the types of phenomena we hope, we will be investigating very heavily for our mission. All right. So I want to talk a little bit about the breakdown of the project itself, how the telescope and the observatory behave. So first, we'll talk about the site and the facility, and that's broken down to our auxiliary telescope and the main telescope. I'll talk about that in a moment. The dome, the mount, and the mirrors. We'll talk a little bit about the camera, and then data management. So as I said, the project's kind of broken down into the stuff that does things and the stuff that handles the data from those things. So over here on the left is the Rubin Observatory as imaged by me in October of 2019. This is a picture I took when I went down to Chile to do some testing in late 2019. And then over on the right, you see the other dome and that hill over there. We call that Calibration Hill. And that's where the auxiliary telescope and a lot of our weather instrumentation is located. And there's a more current view of the site and facility. The dome is actually completed there. There was a delay in the construction process right in 2020, if you remember. Yes, that hit us pretty hard and actually delayed the project quite a bit. But we're up and running. What it looks like in the wintertime. And then the most recent picture I was able to get of the finished facility. So the auxiliary telescope, that smaller dome over on Calibration Hill, used to be a telescope on another peak in Arizona, in Tucson, in fact, but was donated to us in 2008, and then repurposed for its role in on the Rubin Observatory. So what does the auxiliary telescope do? Well, it's mostly going to image the sky to get atmospheric data conditions that can be used in processing the imaging data. And in fact, we expect this data to be kept, and we're gathering so much data and kept for so long that as algorithms change, as the science improves, future generations of scientists can reprocess some of this data, some of this imaging data using the updated algorithms because they have all this weather and atmospheric condition metadata associated with the images to then reprocess based on any new algorithms or technologies that come up. And so this is basically what it looks like. Telescope is inside that dome, and then you can see the red and white pillar with another smaller dome. These are they're just this facility, this hill is just packed with weather instrumentation, cameras for imaging the sky conditions, atmospheric conditions, anything you can imagine, and probably some stuff that we haven't thought of yet. Once we do, we'll add science instrumentation for that. This is what it looks like inside. This is the actual telescope itself. And that telescope has been in operation for years. It actually came online several years ago, and they've been using it to gather initial data and test out the data management processes. So, as I mentioned earlier, the main telescope, the observatory itself, is broken down into the observatory facility. That's the big building you saw out there. And then the Simone Survey telescope. That's, the telescope, the thing that moves, that holds the camera. And those together will conduct the legacy survey of space and time. So just touching on real briefly, Vera C. Rubin was an American astronomer who most notably helped basically helped in the discovery and the identification of dark matter itself. And then Charles Simone is one of the primary donors that helped get the project started off, over 20 years ago. And so we decided to name the observatory after Vera C. Rubin, and then the telescope is named after Charles Simone. Yes, I have a question.
Was Vera C. Rubin a contemporary of Edwin Hubble?
I believe so, yes. Just some more images of the facility. So obviously the telescope itself is located in the dome in the upper portion, and then the rest of the facility is dedicated for housing the equipment that will be used to clean and recoat the primary mirror. I have some images of that facility as well coming up, and you
Are
can
those
see.
windows on the dome?
Pardon?
Are those windows on the dome?
Those are, I forget the term that they use, but they're basically shutters that allow the interior of the dome, temperature and humidity conditions to be finely controlled, because you want the conditions inside the dome as matched nearly as possible to the outside conditions to optimize your viewing experience. So those are shutters that could be opened to control wind and airflow.
How often do you have to clean and
Recoat
Yeah.
the mirror. The plan is to do that every couple of years, 2 to 3 years, depending on usage and conditions.
And they have the facilities there to do the recoding and stuff.
Yes, I'll actually have some images and I'll talk about that in just a few moments. And you can see there's the dome. So the dome isn't the doors open sideways, left and right. It's not a shutter that opens up. And that's what those if you look at the other image, those bars that are sticking out on either side, that's the track for the doors to open. And you can see the mount inside, and then in the very center, that's where the camera would be. This image is old enough that the camera surrogate, the mass surrogate, was still installed. And so this is a rendering of the mount. And one thing you'll notice right off is just how compact it is. It's very stubby, it's very short. And this is what allows the telescope to move so rapidly. The longer your telescope is, the more time and care you have to take to move it around the sky. We want to be able to move to any arbitrary patch of the sky in a short amount of time as possible. And so we're talking, you know, a 3.5-degree slew in just a few seconds, much more quickly than most telescopes. And this is a large telescope. I actually have some videos in a few moments. You actually see the motion of this compared to one of the other telescopes that I work for. There you can get a sense of the scale of this thing. This is a large telescope.
Wow.
That's what I said when I saw it. And I mean, this picture doesn't do it justice. When you get there, it's huge. All right, so that's another view, and I have a video coming up next. Yes, so hopefully this plays okay. There's some background noise, but I have it muted for the moment. You should see.
Yeah,
Little choppy on the Zoom call. But you definitely get a sense of just how rapidly this telescope moves.
That's real time, that's not a time.
That's real time. Yes. The choppiness, I think, is from the streaming over the Zoom call.
So it's constantly taking digital pictures.
So it'll move to a whatever location they want to image. And the plan is to take 30-second exposures. So it'll move to a patch of the sky, take 1 or 2 30-second exposures, and then move to the next target. And a lot of the operations will be automatically controlled. There will not be somebody at the controls telling the telescope, go point here, take an image, go point here. It's much more automated than that. They'll have a planned mission program for each night, and the computer will do most of the controls of pointing and taking the images. Yeah.
So, understand as a survey telescope, it's their program, but like, let's say something interesting happens in the night sky. And they say, let's put the, schedule program on hold and go take a picture of said interesting thing.
Yes, absolutely. Couple of things. Obviously, the telescope, the scheduled observations can be manually canceled at any time. Observations can be inserted into the scheduler, is what we call the process for controlling that process. And we're tied into all kinds of networks around the world, so that if an interesting event occurs, a supernova or something, the scheduler can actually get that information and immediately react to it without human intervention.
wow.
I'm not sure how well that's been tested yet, but certainly in simulation,
Yeah.
it's worked. We haven't had the opportunity. I mean, we've only been up and running for a few weeks, but yes, the idea is if a facility somewhere else indicates that there could be a supernova somewhere, the computer will actually get that information and then preempt all the other observations and immediately move the telescope to that event to start imaging. Yeah.
Is there a limit to like how close an object the telescope can focus on? Like, if there was an asteroid passing by, like, pretty close to Earth, would it be able to like actually focus on that?
The short answer to your question is no. And you'll see why in a few moments when we talk about the actual imaging parameters. I have to jump out of the full screen for the next slides because the videos don't play well for some reason. But this is one of the other telescopes that I work for. This is the one on top of Mount Lemmon, the one that Vanessa and I work on. And I took some videos of this telescope moving so you can kind of compare. But keep in mind, the one you just watched moving is more than 8 times larger than this one. So the one you just saw is 8.4, is an 8.4 meter telescope, and this is just a 1 meter telescope. But you can get a sense, just a 1 meter.
Is that a commercial telescope?
No. This was custom built for our facility.
That real time.
That is real time. So again, you might say, well, they actually moved at about the same rate, but the Rube Observatory telescope is more than 8 times larger than this. So you're talking of, many magnitudes larger, more massive, and we're still moving almost, if not faster, than this much smaller telescope.
We said that was a 1 meter.
Yes. So that's the one Vanessa and I worked for. That's how we met. So this is from when I was down in Chile in 2019, doing some testing. So this is the mirror cell is the blue box at the bottom, and then on top that white, that's the mirror surrogate. So it's a mass surrogate. We didn't want the glass on there when we were doing our initial testing. When you're talking about an 8.4 meter telescope made out of 1 meter thick or more of borosilicate material, this is a massive, many ton piece of glass. And as the telescope is changing its position in the sky, as you're pointing straight up to pointing at the horizon and anywhere in between, the gravity actually deforms the glass. So you're going to get denser, you would get denser towards the bottom, and then obviously less dense at the top as the gravity shifts. And so that mirror cell, that cell under there, contains hundreds, dozens of actuators that are supporting the weight of the mirror and can actually counteract the gravitational deformities or the deformation caused by gravity on its position in the sky. This is called active optics. So this is a little bit different is much different than adaptive optics. So adaptive optics is designed to account for atmospheric aberrations in order to get the most clear resolution of a patch of the sky as possible. Here, kind of to answer your question about being able to focus on an object, we're not focusing on one object. Our field of view is quite large. And so we don't need to be able to resolve smaller objects, but we want the sharpest image we can get on a wide field of view. So we have to support the weight. So we use the active optics system to support the mirror and counteract any deformations as we change the angle of the mirror. And that's what that cell is doing. It houses all of that, all those actuators and materials. So in Tucson, at the University of Arizona, we have a football team. Fine. Much more importantly, underneath the football stadium is the Richard F. Karras Mirror Lab. And this is where a lot of the world's mirrors are ground. They're actually made in the facility underneath the football stadium at the University of Arizona. And not only do they make the mirrors there, but they actually do a lot of the initial testing to make sure that it's coming out to spec. And so I actually had the opportunity to go test out the mirror at the mirror lab before it was shipped to Chile. And that's what you're seeing here. This is an actual image of the mirror that very similar look and color to the surrogate, but you can see that there's actual shiny surface at the top, and then it's the same cell, that bluish green color at the bottom. This is a top-down view of the glass as well. And then this is our secondary mirror. We'll talk a little bit about the mirror construction in just a few minutes. But that's kind of gives you a sense of the size of the secondary mirror. And then here is the secondary mirror after it was coated with the materials. Oh, actually, I guess I should talk about that. So there in the back, that big metallic disc in the back, that's the coating chamber. So both the primary and the secondary mirrors, in turn, will get brought from the dome down a large elevator and then tracked out. That's the long part of the facility you saw earlier. One of the levels contains the coating chamber, and so the mirrors can be brought down moved underneath the coating chamber. The chamber will come down on top and then strip away the old coating, clean the mirror, and then deposit a new coating. We'll do that every few years. So that's what that gangly looking thing in the back is. That's the coating chamber that'll be used to clean and recoat the mirrors periodically. So to achieve the compact design that we have, in order to get that compact design, the primary mirror, let me go back a couple of screens here. The primary mirror, I'm not sure if you can see it online or in the screen, but if you look kind of in the middle, you can see another circle in there. It's because this mirror actually has two different concavities. M1, it's called the M1, M3, mirror 1, mirror 3. And what happens is the light comes down, hits the outside concavity. The light gets bounced back up to the secondary mirror. Light gets reflected back down to the third mirror, the other concavity on the primary substrate. And then the camera is actually located in the middle of the secondary mirror. Yeah.
I know you said you didn't know anything about optics, but at that facility under the stadium, they do spin casting, right? But they didn't spin cast it this way. Is this part of the grinding that you got the outer and the inner?
Yes. Yes.
Okay.
Yes. Yeah. And then here's a 3D rendering so you can kind of get a sense. And so that popsicle lollipop shaped thing of the middle of the secondary mirror, that's the camera. So the camera is the largest camera in the world. It's actually in the Guinness Book of World Records. It's a 3.2 gigapixel camera. There are 6 optical filters, so it is taking data in optical wavelengths. And then 5 of these can be in use at any one time. And so getting to your question about focusing on any one object, the field of view is the equivalent of 45 full moons. We have a giant field of view. And you'll get well, I have a depiction of that coming up in just a few moments, but you can kind of get a sense. The camera is about as big as a person. Many lenses, many filters, and then all of the electronics you need are all built into the camera itself. That's the actual lens, the primary lens. And then here's the actual camera in SLAC, the Stanford Linear Accelerator Lab, just before it was shipped to Chile. The camera is on. We're just about to start our operations. We'll talk a little bit about that towards the end of the project. So we have a 3.5-degree field of view. And we're completing a scan of the sky every 3 days. Most of the telescopes I know take weeks or months to complete a full scan of the sky. We're going to do it every 3 days. And we're going to generate 20 terabytes of data each night. So there you go. There you can kind of get a sense. So Gemini is one of the facilities located right next to Rubin Observatory. Roughly the same size primary mirror, about 8 meters, but you can see a stark difference in the field of view. And so now it's on to the software. So we've talked a bit about the facility and how all of that is constructed, but what do we do with all of this data? Well, as I said, we're looking for differences. We're looking for transient events in the night sky. So objects that change brightness or position on short timescales. And since we're generating 10 million alerts per night, people can't process that data in any meaningful way. So we have software that's going to scan these images. Each time we get a new image, it's going to make comparisons to images of the same area from the past. And then anything it detects as a change will generate an alert. Some of them will probably be false alerts for various reasons, but the software is not, it's going to generate these alerts. It'll do its best to make sure it's alerting something of significance, but we also want to be pretty liberal in what does get an alert, because we'd rather get too many alerts and some false alerts rather than miss something significant. Data is transported over 2 dedicated fiber optic cables. Yes, we built trenches and laid fiber optic cable from the peak and Cerro Pachon all the way to the data center here in the United States.
You have to dig.
They, for obvious reasons, have not advertised much of that. They don't want anybody, messing with it. So, I mean, I don't think it's that deep, but I don't know the details of the fiber optic cable system. This graphic is a little out of date. Up in the upper left, you could see it indicates that there's a data facility in the upper Midwest of the United States, in Chicago. That was an old location for our data facility. That's actually now been moved to Slack, so over in the left. So you can just imagine those 2 points up in the United States are now both over in the California area. But this is essentially how the data will flow from the facility in Chile to the data centers where the data will be stored and backed up. And then there are backup facilities as well. So the data will be stored and backed up to prevent any issue in any one location from disrupting the data as a whole. Kind of example of what a data center looks like. I've actually been to the data center. It looks pretty much like that. It's just banks and banks and banks and rows and rows and rows of massive computers.
And there's total redundancy there.
This facility, yes, and then we also have backup facilities as well. So the data will not be stored at any one location. It will be stored in multiple locations and on multiple servers as well. All right, we are currently, as I kind of mentioned, we are currently finishing construction and commissioning. Because of the pandemic and affecting the schedule, we didn't end construction and then start commissioning. We kind of ran both of them together. As we're ramping down construction, we were also beginning to ramp up commissioning. But we had our first photon on the 15th of April of this year. And in fact, the image you can see on the right is an image I took of from our control center in Tucson. And over there on the right, that is the first data that came off of the camera through the data management system and onto those screens. So I was there. I got to hear the cheers of everybody. It was a pretty cool time. First science light is soon. And when I say soon, they may have already done it. I actually am on vacation, so I'm not on the Slack. So I don't know if they actually have done it yet. But when I was finishing up these slides the other day, the date of first science light was like a few days ago or something. So if it hasn't happened already, it should be happening any day now. And then our operations readiness review is scheduled for mid-September. Assuming we pass that review, and we have no reason to believe we won't, we will begin operations at that time. But I can send you a link to the status page that is kept up to date. And then this data is up to date as of just a couple of weeks ago. So to sum up, we have a very large field of view. So we're not interested in focusing on any one particular object. We want a large swath of the sky so that we can generate as much data over as large a field of view as possible, and then be able to compare those images over time to detect small scale changes in the night sky. Hence our compact design to achieve that goal. The 3.2 gigapixel camera, though, does give us comparable resolution to some of these some of the telescopes with much smaller field of views. We have a 10-year primary mission. We expect to generate over 500 petabytes of data That data should include something around 20 billion galaxies, 17 billion individual resolved stars, 6 million orbits of solar system objects, 10 million alerts per night, and it will take decades, if not longer, to analyze that data. There are graduate students whose parents haven't been born yet that will be analyzing data from from the Rubin Observatory. And so it really is a unique telescope with a very unique mission.
20 billion galaxies.
20 billion in the, yes, of what we can see. And so that's me. You can see Calibration Hill over on the right, and then over on the left, as I said, there were a couple facilities that share. So I was standing right next to the main telescope. You can see the auxiliary telescope in the distance on the right there, and then Gemini over there on the left. And then, so that's the end of the talk portion of the project. I do have a link to some of the first look images if you wanted to discuss or ask questions about any of those. But I assume most of you have seen them and may actually know more about some of that stuff than I do. I'll click on the link. And then at this time, I can field questions, or we can start clicking around on some of these first look images and take a look at those.
Is that the Trifid Nebula?
Trifid and Lagoon nebulous. Yes, I don't know what galaxy that is. I clicked on the link earlier and it doesn't specifically give a name for the galaxy in those images. I guess what I can do is bring up, which is the one I really like. I think it's, yeah, that one. We'll bring up this one. So this is the full image that was used for the first look images, and only a portion of it was used in the press conference. In fact, I believe it was this part here towards the bottom. It's used. Let's see, there's an image in here I know that contained, there it is. There it is. Yeah. So this is the full image that was used in the press conference, and then a chunk in the upper right-hand corner with that triple interacting galaxy. That was what was cut out and then presented at the press conference as the very first image. Could be. Yes, sir.
What are those two? There's one in the center and one on the left. The ones with, so like 4 red lines coming out.
That is probably a foreground star. Again, this is where I am not an optical engineer.
So what's the payoff for the Department of Energy on this? It doesn't seem to make a strong connection for me.
Well, they got to build the world's largest camera.
Okay, so
Otherwise, that's all political machinations. Yeah.
high-level scientists to do high-level tasking.
Well, Slack had the facilities and the people to design the camera. Aura has the facilities and the capabilities to set up and design the facilities and the structures.
We have a question in the chat. Are the filters narrowband? Are they on a filter wheel or some sort of interleave structure?
They're on a filter wheel. And I don't know about the bands that they're using. They're optical bands. So what's that? Question in the back.
Oh, could you go back to the gallery? Scroll a bit, because I think like one of those videos, within a circus like that, circles, that's like tracking the asteroids.
This one is actually variable stars. We can actually start playing some of these. So this particular one is tracking variable stars. And then the one you're referring to, I'll bring that one up next. There is music playing if you want to go click on these in real time. So 30% brightness change in just a few hours. 11% brightness change in just 10 minutes. So, I mean, these are effects that haven't really been observed because these objects, maybe as a singular object have been observed that way, but as a whole, we know we're missing many others. And so the idea is to be able to track and capture these much more rapidly, much higher rate, being able to identify those. And so the one you were referring to with the asteroids is actually a lot scarier. Yes, Ruben we haven't even started operations and we've already revolutionized near Earth object detection.
Like, how many magnitudes more data is this than something like the Whitney transient facility or something,
100 times.
100 times more?
Yeah. On top of Mount Lemmon, where our telescope is located, is the Catalina Sky Survey. We actually share a peak with the Catalina Sky Survey. And they're at the leading edge of near-Earth object detection. They observe hundreds of objects each night and detect dozens of new objects also each night. We're going to blow that out of the water just because of how rapidly we're imaging the sky. Yeah.
With all this data, unprecedented data,
Yes.
obviously a lot of the image recognition is automated. Could you comment on two things? One, to what extent are you using AI or deep machine learning to identify objects? And the other is, I'm wondering if this facility uses maybe a local cloud to store its data.
So I'll answer the second question first. We are required to have a 30-day store on the summit. So we have a copy of the data from the last 30 days on site. So if there's ever any disruption, we can re-upload data as necessary. As for the former, as a survey project, we do some of the analysis, but the data is actually made available to the public on a very regular basis. And so as far as I know, our project is using software, but not AI per se for detections. Now, what citizen science folks do or what other institutions will do when they get access to the data, that's up to them. But to my knowledge, currently, we're not using AI, but we do have software in place that is doing. Maybe that's a distinction without a difference. I don't know.
Another
30
question.
days of data on site.
Yes.
And then beyond that, the data gets stored offline.
Yes. So the US data facility at SLAC is where all the data will be stored. All 500 petabytes of data.
Another question from the chat. What sort of strategies are used to deal with artificial satellites?
We have people in discussions with various institutions to discuss the best mitigation strategies. We are at least attempting to get orbital data for these satellites so we can try to optimize our imaging to avoid satellites being in the images. As far as the satellites being designed in a way to minimize their impact on astronomy viewing, that may have been the case in the past, but that is no longer the case. So a lot of it is doing our best to study and understand the characteristics of the various satellites in the hopes of being able to eliminate that data from the raw data, or at best avoid areas where satellites will be, and that will get factored into the scheduler process for imaging. I wish I could give you a better answer, but I can't. Yeah.
Is Ruben's capability gonna be potentially threatened by that power plant that they're building and rebuilding?
I've heard some discussion. We don't think so. Possible vibrational effects, perhaps. But we honestly don't really know yet what effects that facility might have. Not fully, anyway.
It's nuclear or water hydro or what?
I actually don't know. I don't remember the details of that facility. Yeah.
Where do you get your power from? All the time.
I believe we're tapped into like we have a giant generator that can keep the telescope up and running for about 3 days. But we do rely on city infrastructure, national infrastructure for our power. But
How is the backup data for the other 27 days?
those 3 days are for like operations. Basically give us an opportunity to either shut things down properly, because it can take a lot of time to shut these things down if the power outage is going to be extended, or be able to carry on full operations for a short period of time until the power comes back online. But if the power outage will be long enough, they would suspend operations and use the power for maintaining facility conditions,
They
basically.
would be safe, shut down the system.
Yeah, exactly. Keep the data centers up and running and cooled, and not do much else.
What's the elevation?
Almost 9,000 feet. So not that bad. It's actually interesting. The Mount Lemmon Sky Center telescope is a little bit higher, actually. It's about 300 feet higher than Sir Butcher.
So as far as like, it seems like it's really well maintained and in comparison to, we heard earlier this year about what a catastrophe has occurred in Arecibo and Puerto Rico as far as lack of maintenance and lack of being on the ball. So they seem to have their stuff together now. I'm assuming it's a consortium of all kinds of Europeans and Spaniards and French and in addition to the Chileans and Americans,
For
staff that we saw.
For the funding or the maintenance of stuff?
I'm sorry,
For the funding?
no,
Or-
not for the funding, just for personnel on site.
Oh, so a lot of, yes, most of the folks up there are going to be Chileans. We hire, most of the Chileans will do the engineering, the construction. The dome was built by a team out of Italy. So they had some folks there on site handling the construction of the dome. That's pretty much done, so they've left. Spain, there's a company in Spain that handled constructing the mount, the mount assembly. And so they were there about the same time I was getting the mount set up. But they're done. But the day-to-day operations are mostly handled by local Chileans, and then whatever scientists or astronomers from the project are on site. But most of the staff is Chilean.
So they have like a dormitory there? Or
Mhm.
is it?
Yeah. There's a limited amount of facilities located in the building itself. Those would mostly be for the on-site observers. So once operation starts, during the day, there could be a couple dozen people on site, maybe, and then overnight, there's only going to be a handful, 3 or 4 or 5 people on site. So there's only enough facilities for maybe a couple of people to sleep in the building itself. And then there's a larger facility offsite on the mountain, but off the peak, that can house, 20 odd people. But that facility is designed for all of the facilities to access. So we have to coordinate very heavily. And then there are buses that bring everybody up each and every day.
How far to your nearest pizza shop or taqueria?
There's a lovely cafeteria on site, actually. There are several cafeterias on site catering to all the various buildings that are up there. But then the city of La Serena is about an hour away from the peak, maybe a little bit less, depending on situations right there. And that's a full-on city. When I was down there, I would walk to the mall and get my Starbucks. So all the beach right there. It's pretty nice. Pretty nice place.
Well, we want to thank you.
And thank you very much. This was a lot of fun.
We're waiting for.
Thank you. Thank you very much.
And if you, is your family still here? I guess they are. If you would leave.
Okay.
We'll probably do the business.
Gotcha. All right, we'll see what they're up, but I'll hang around for a few minutes just in case there are any last minute questions or if anybody wants to come say hi in the back.
All right.
Do you see the funding as being secured for this?
With what, a 10-year mission?
Who knows? The best answer I can give you, and I'll say one of the things I really appreciate about my company and my project is they've been very open and very communicative about the situation, and they're just as much in the dark as any of us are. We're already built, the money's already promised. Canceling those contracts would probably cost the federal government more in the lawsuits that would result than it would be to just continue the funding. But we have been disrupted. People are traveling less because it's harder to get the travel funds and things like that. So as far as I know, the first 10 years are certainly funded, and likely nothing will change with that, or at least not dramatically or significantly.
We're gonna take a 10-minute break. If you have additional questions, feel free to ask, but also if you've not signed in yet. do
Sure, off
so.
earlier, but I got a little spot on it at the restaurant, so I changed. Yes.
Please partake of refreshment.
Like, how much does it cost to operate and maintain it for like a day or a month at a time?
I